So far, we've been solving systems where everything's all hunky-dory. Everything's fine. Everything's happy. We're going to talk about some ways that things can look a little odd. Okay. So we have some definitions. These aren't super important, but just have them if you need to refer to them, but not super important. So below are some definitions. We're going to draw some examples of each. So a consistent system has at least one solution. So we've been having that, right? All of our examples have been consistent systems so far. We've all had solutions. So, maybe that system has, one equation that looks like this, one equation that looks like this, and there was a solution here. It's consistent if it has at least one solution. Well, let's skip all the way to number 4. If a consistent has at least one, an inconsistent having none, that kind of checks out. What does a system of linear equations with no solutions look like? Again, let's label this one. What does no solutions look like? How can two lines never cross? Well, we've seen that before, right? I'll write it down here. Two lines never cross if they're parallel. So that's what an inconsistent system might look like. An independent system has exactly one solution. Again, this is really what we've been working with in this section. Maybe one looks like this. Maybe the other one looks like this. There's exactly one solution. A dependent system has infinitely many solutions. What would that look like? We haven't run into that yet. 3 and 4 are really what we're going to focus on in this video. What does infinitely many solutions look like? It means the lines cross at infinitely many points. How can two lines cross at infinitely many points? Well, if this is our first line, then this is our second line. They're the same line, okay? So we'll have and you might say same line, that's silly. But maybe we have something like this, right? Maybe y, the first line is y equals, 1/2 x plus 1. What if our second line is 2y equals x plus 2? So they don't look the same. But notice, if you multiply the blue line by 2 on both sides, you get the red line. So even if they can be the same equation, they can be the same line, without being in the same form. Okay, so that's what number 3 could kind of look like. We'll see that. Example 77. Whoa. Have you been sleeping? Did you miss the previous 70-something examples? No. I just forgot what example number we were on when I was making the notes, and I had 2 options. I could either scroll up one page or make something up. This one was easier. So we're on example 77 now. Solve the following system of equations. And again, there's a lot of different ways of doing it. Which one makes the most sense here? Graphical? I don't really like the graphical method. I didn't sabotage the notes on purpose, but we saw why graphical can sometimes not be so good. So let's either do it by adding or substituting. Both are fine. But substituting is quicker here. Why? Because we already have a variable solved for. If you already have a variable that's solved for, substituting is real quick and nice. So let's substitute this into the second equation. So we know that x is 9 minus 2y. And we know, so we're going to just plug that into this. We're going to plug that right-hand side into this x into the second equation. We have x, which is 9 minus 2y, plus 2y equals 13. Let's simplify and solve for y. 9 minus 2y, nothing fancy to do with the parentheses here. Minus, we have negative 2y, we're adding a 2y, now we have 0y. I'm feeling a little uncomfortable. I'm feeling a lot of uncomfortable. What's going on here? 9 is equal to 13. No, it's not. No, siree, this is not true. So don't panic. What does a solution to a system of equations mean? The solution to a system of equations is the point that makes both equations true. What do x and y have to be to make this true? What does x have to be? And what does y have to be for 9 to be the same thing as 13? When is this going to happen? Never. I don't care. There are infinitely many values. I don't care which of those infinitely many values of x and y you choose. This is never true. Never. 9 will never be 13 in our mathematical system. Okay? Regardless of what x and y are. There's no solution here. Right? We could consult our definitions and say that this is an inconsistent system. I'm really not going to use these words very much, but we could say that. This is an inconsistent system. And indeed, right, if we did try to use the elimination method, we added 2y to both sides, our first equation would be x plus 2y equals 9. And our second equation would be x plus 2y equals 13. And again, you can see that the left-hand side is always going to be the same and the right-hand side is always going to be different. If we eliminated, we get something equally silly. If we multiplied one of these by a negative and added them together, the other method would give us the same result. If you graphed them, what would it look like? Parallel lines. They have the same slope, but different y-intercept. Let's do another one. Example 78. Do we want to use elimination or substitution? I like elimination here because they're already lined up, right? All the variables are on one side and all the constants are on the other side. So it's prepped. I was always taught it as being called the elimination method. I mean the addition method. Solving equations by adding is the lingo that this book uses. But I learned it with a different term. Okay, so we need the coefficients to be opposite. So notice that if I multiply this first equation by -3, we'll have a -3x, and those coefficients will be opposite. We can add the equations together. So if we do that, we don't need to do anything to the second equation. The second equation can just chill, relax. The first equation, if we multiply everything by -3, we get -3x minus 9y equals -6. I think you might be able to see where this is going. Let's add these equations together. -3x plus 3x, well, we don't got any x's anymore. -9y plus 9y, well, we don't got any y's anymore either. -6 plus 6, well, what does this equation simplify to? 0 equals 0. When is this true? When is this 0? When is 0 the same thing as 0? Well, that's always true. I don't care what x and y are. This is true. Any x makes this true. Any y makes this true. I'm going to draw a smiley face. There are infinitely many solutions here. And there is one small... This is usually the answer we're going to get, but it doesn't actually mean that any xy pair makes this true. There's infinitely many solutions, but x plus 3y still has to be 2. They're the same equation, but we still have to satisfy that one equation. So this is the answer, and you can put this as your answer, but technically I just want to make sure, right? This is right. Any x and y with x plus 3y equals 2 is true. Okay. Like we said over here, this is a dependent solution, infinitely many points. So anything on this line makes it true, but this solution This is not a solution, for example, right? Just anything on that line. But they are the same lines. All right. Now we've done all the, it's been smooth sailing. And in the next one, we get into some more interesting stuff. Enjoy.